the last topic in the series of applications of Gauss law to different systems is the application of Gauss law to find the properties of conductors in electrostatic equilibrium. For this purpose, we have first to define what do we mean by static equilibrium. Now, a conductor will be in static equilibrium if there is no net movement of the charge within the material of the conductor. You know, even if you put a charge on a conductor, then there is an excess of charge on that conductor. Now, static equilibrium is that when this charge gets distributed so that there is no movement of the net charge. Why I say the net charge? Because, you know, as we have said when we discussed the properties of conductors, the electrons in the conductors are in continuous random motion, but there is no net drift of electrons from one part of the conductor to the other when the motion is random. Therefore, if there is, for example, a positive charge with a deficiency of electrons, and this positive charge gets distributed in a given way, that distribution of charge is static. Although the electrons, the charge carriers, which are the electrons, are still moving, but that motion is random, so that this static distribution of charge doesn't change. This is the state of static equilibrium. Now, when we talk about electrostatics and conductors in electrostatic applications, we will always assume that the conductor is actually in static equilibrium. As we will see, conductors switch when they are even in non-equilibrium state, they switch to the state of static equilibrium very, very quickly. So this is what we mean by a static equilibrium state. Okay. Now, as a consequence, when we have an electron, a conductor, sorry, and it carries a charge, and that electron reaches the state of static equilibrium, then as a consequence of this, we have some properties. Okay. The first property is that as a result of the static equilibrium, when we take for given that, okay, the conductor now is in static equilibrium, the electric field inside the conductor must be zero. We will prove this. The second property, if the conductor carries a charge, that's if it's charged, then the charge just outside the surface of the conductor, okay, so it's inside, it's zero. What about outside? Just outside, that's just at the surface from outside, the electric field there is normal to the surface. Okay, these two properties follow from the concept or from the static equilibrium distribution of the charge on the or within the conductor. Now, there are other properties that we will be proving also for conductors in static equilibrium using Gauss law. What are these properties that we can prove using Gauss law? The first is that if the conductor is isolated, that is, it doesn't have contact with its environment, the charge inside the conductor cannot move outside, or no charge can from outside the conductor can move into the conductor. If that's the case, then the charge resides on the surface of the conductor but not within the material of the conductor. And this is true even if the conductor is hollow, like for example a shell. The charge here, as we will show, will reside on the outer surface of the conductor. The other property is that the electric field just outside the conductor, which as we have said will be normal to the conductor, has the value sigma over epsilon naught. So above a given point, just outside the surface, the electric field will be equal to the charge density below that point divided by the epsilon naught. Okay? And a final property that we will need to prove later is that when you have an irregular conductor, then the charge density will not be uniform over that conductor surface, but it will be higher when we have edges. In other words, when the curvature of the parts of the curvature of the conductor which have higher radius of curvature will have less charge. Those which have smaller radius of curvature, that is more narrower, these will have higher charge density. Okay, this will need to be we need to wait for later to be proven, and the electric field also therefore will be stronger when you are near these edges. So let's move to proving these properties one by one. Let's start with the first property, which is the electric field inside the conductor is zero. And to understand, to do this, let's consider a situation where I have an electric field, and it might be a uniform electric field in some region in space, and then you bring a conductor, a conducting slab, originally uncharged, okay, and you put it in that electric field. Okay, so I have a region where I have electric field, I bring a conductor, I put it here. Okay, now this is the part of the space that has been occupied by the conductor. Now before, in this part of space there was electric field. When you put the conductor, the electric field inside the conductor, okay, in the space that we used to have electric field, is now zero. Okay, this is the first thing. Now why is this? We will explain the mechanism, but I mean, as far as long as the equilibrium, as the conductor goes into static equilibrium, then in this case the electric field inside it, when we accept this, that okay, after you put it, immediately or very quickly it goes into static equilibrium. In this case, the electric field must be zero as a result of static equilibrium. Why is this? Because if it were not in static equilibrium, then the charges inside would experience a force, okay, acting on them. And if they experience a force, then these charges would accelerate. But charges accelerating, this means there is a net movement of charge, and therefore this is not static equilibrium. So if you assume that as you put the conductor into a region and this conductor moves immediately to the state of static equilibrium, then definitely the field inside cannot be anything except zero, because otherwise the charges would be moving because there would be a net force acting on them, and then there will be no static equilibrium, which is contrary to the assumption that your equilibrium reaches, your conductor reaches the equilibrium state in this case. Okay, so this is the general argument, but the question of course is what happens exactly. What happens is the following. Now when you apply, when you put the electric field, the conductor and the electric field, now there are free electrons inside the material of the conductor, as everybody knows. Now these free electrons would be attracted by the electric field, and so they will move to this side of the slab. They will leave behind them a positive charge on the other side. Well, the result of this, that inside the conductor you will have another electric field, and this electric field, the charges will arrange themselves in a way that the electric field induced now due to this polarization is exactly the electric field needed to cancel the electric field inside. So this is exactly what happens. Okay, therefore the fact that the electric field here is zero and we have in static equilibrium is a result of the fact that the conductor becomes polarized, and you will have a positive charge here, negative charge here, and they will have another electric field which cancels the already electric field that used to exist here. You remember, originally in this vicinity of the charge we had an electric field. Now with the new setup, with the polarization, this electric field is cancelled. Of course, as a result, this means that we have an induced charge, so there is a charge density actually on the conductor. The whole conductor is still neutral, but there is a polarization and we have an induced charge here. So this is why we have a net zero inside the conductor. Therefore, we take it as granted that if you are in static equilibrium, then whatever type of conductor you have, charged, neutral, neutral in electric field, or whatever, the electric field, once what happens is that the charges redistribute themselves so that the electric field inside the material of the conductor is always zero, because otherwise you will not have a state of static equilibrium. So this is the reason behind that. Now, how long does this process of redistribution of the charge to restore static equilibrium takes? In a typical conductor, this is of the order of 10 to minus 16 seconds, which is almost, this means for all practical purposes, this is almost instantaneous. Okay? Even if the conductor is hollow, the electric field inside it is still zero, inside the cavity of the conductor. That's outside the material of the conductor, but within the conductor is still zero. We will discuss this later when we consider the potential. Now, we move to another property 3, which is if we have a charge on the conductor, then that charge will definitely reside on the surface and it will not remain within the material of the conductor. To prove this, this is a conductor and we have a charge on that conductor. Okay? Now, we take this blue line here that you can see, we take a Gaussian surface. This is your Gaussian surface. Now, this Gaussian surface is arbitrary. Take any Gaussian surface so that this Gaussian surface resides entirely within the conductor. Now, the electric field inside the conductor is equal to 0. This is because it is in static equilibrium. Okay, even if you have a charge here, the electric field by default, if it's in static equilibrium, it must be equal to 0. So we know that at the Gaussian surface, the electric field is equal to 0. Therefore, there is no net flux through that Gaussian surface, because the electric field at the surface is equal to 0, and so the flux through that Gaussian surface is equal to 0. This means there is no charge inside that Gaussian surface. So the net charge inside the Gaussian surface is 0. Now, this Gaussian surface can be taken as close as you like to the surface, given that it is just within the material of the conductor, just below the surface. And so there is no charge inside such a Gaussian surface, and therefore there is no charge anywhere on the conductor apart from the surface. Okay? So there is a charge. We know that there is a charge on this conductor. We have charged this conductor, so there's an excess charge, positive or negative. But we've proven, if the electric field is 0 inside the conductor material, then that charge, we are taking this Gaussian surface to be just below the surface, okay, and because the electric field is at that within the material of the conductor, even just below the surface, is 0, then the flux is 0, and so the charge is 0. So there is no charge within the material of the conductor. Where it is then? Oh, it is on the surface. So this is that property. Okay? Gauss law doesn't tell us what is the density of the charge or how it is distributed on the surface. Just it tells us that there is no charge that is the within the material of the conductor, and the charge is exclusively on the surface. Now, the second and fourth properties that we have just discussed is that if there is a field, that the field must be perpendicular to the surface. Okay, and we will find what is the magnitude of that field. Now, why the field must be perpendicular to the surface? In other words, if this is a charged conductor, carries a charge. Now, we have seen that this charge should be distributed over the surface of the conductor. There is no charge inside. Inside, the electric field is 0. What I'm saying is that the electric field should be always just near the surface, should be all normal to the surface. So this is how the electric field lines look near the surface. Okay? This angle is always 90 degrees. It's always 90 degrees. Now, why is this so? Well, this goes with static equilibrium. Because static equilibrium means the charges, the net charge, is not moving. Now, so the charges are on the surface. If I have a component of the electric field parallel to the surface, then these charges will feel a net force, and they will move, and the charge density will change. The charge will not be static anymore. Okay? But I'm assuming that it's in static equilibrium. Therefore, under static equilibrium condition, there can be no component of the field parallel to the surface where the charges reside, so that, because otherwise the charges would be moving, which is against the static equilibrium. And therefore, the component of the electric field just at the surface, near the surface, should be always normal to the surface. Because only then the charges, they will experience a force, but this force will not the charges will not be moving. If I had a component in this direction, the charges would flow along the surface of the conductor. Again, this is true only in static equilibrium. If the conductor is not in static equilibrium, then this is of course not true. There can be an electric field at the surface, and this electric field can has component parallel to the surface. And this is how current flows. But when current flows, we are not in static equilibrium. Okay? So this is the thing that we have to keep in mind. In static equilibrium, a conductor, charge carrying conductor, will have its electric field normal near the surface, normal to the surface. If the charge were negative, then the only difference will be that these arrows will be pointing towards the conductor rather than away from its surface. Now, what about the magnitude of the electric field? Well, to find it, we apply Gauss law, and we take this as a conductor, and we take this as a Gaussian surface. Okay, this is the small cylindrical box, and you can see part of this box is penetrating within the material of the conductor, and the other part is just going out of the surface. Now, what we know about the electric field here from before is that inside this part of the Gaussian surface, which is penetrating the material of the conductor, the flux is zero because the electric field is zero. These curved surface, the cylindrical part of this surface, there is no flux through it because the electric field is normal to the surface of the conductor, and so it's parallel to this surface, and so it's perpendicular to dA, and therefore there is no flux through this surface also. Okay? And therefore, if I apply Gauss law, then the net flux through this surface will be just the flux through this part of the surface. Okay? Here I have no flux because the electric field is zero. This curved surface will have no flux through it because the electric field lines are parallel to the surface. The only flux will be through this. And E here is normal to the surface, and it's parallel to the normal vector here. And so the flux will be EA. And what is this equal? It's equal charge enclosed. What is the charge enclosed? It is the charge on a disk that cuts the surface of the conductor, which is equal charge density multiplied by A divided by epsilon naught, and from which you get E equals sigma over epsilon naught. This is a very general result. Whenever you have a conductor of any shape or size or whatever, and the conductor carries a charge, this charge is on the surface, the electric field is normal to the surface, and the charge above a given point is given by sigma over epsilon naught. Sigma is the charge density below on the surface, below the point where you are finding the electric field. Okay? This is a very general result. Sigma, of course, doesn't need to be constant. I mean, unless the conductor is symmetrical, like a sphere, for example, where the charge density is uniform, the charge density on the surface of a conductor does not need to be uniform. And therefore, sigma is not uniform, and the electric field, therefore, is not uniform. It's just as what we have seen. The electric field is actually sharper near the edges. Now, near the edges here, the charge density will be higher, okay, when you have sharp edges. So you can see here the charge density. The radius of curvature is large here, the radius of curvature is small here. So the charge density here is smaller than the charge density here. Therefore, the electric field in this region above these points is stronger. Okay? And therefore, you will have stronger electric field here. This is how it will look. Now, let's consider an example saying, for example, in this case, you have a conductor, and this conductor has a cavity inside it, and it carries a positive charge Q. Now, what is the charge on the inner surface of the cavity? That is, what is the charge here in this case? Okay? So this is exactly the same conductor as before, except now it has a cavity. Now, the question is, okay, what we have proven is that if you have a conductor, then the charge resides on the surface. The question is, does this include this inner surface, or will this charge reside just at the outer surface? Okay? This is an example of an answer, a question that can be answered actually using Gauss law. Well, how to apply this? Well, consider a Gaussian surface. Take this Gaussian surface here. Okay? And this Gaussian surface now is within the material of the conductor. Since it is the material on the material of the conductor, then the electric field at the Gaussian surface is 0. And therefore, the flux through the Gaussian surface is 0, because the flux is the integral of the electric field around the surface. And since the electric field at the surface is 0, then that integral is 0 and the flux is 0. This means that this is what does it mean? When E is 0, then the whole thing is 0. Okay? And so the charge enclosed by that surface is 0. So there is no charge on the cavity, because you can take this as close as you like so that it is just above, still in the material of the conductor, so the electric field is still 0 on the surface, but it is just above the surface of the inner surface of the cavity, and therefore the only charge that encloses in this case is that on the surface of the cavity, and there is no charge